Hello, everyone. Um, Thank you for joining back. Um, as James mentioned, we will continue with the second part of Module 2.1, implementing viral infection model in CC3D, implementing infection and type transitions. Um, I wanted to go ahead and include in the chat the link to the files that we will be working with today. As I mentioned yesterday, we are using um, this directory to provide versions of the code that correspond to each module, such that if you do not, if you are unable to walk through the building of the model in one module, you can continue from the next version on and then go back to the videos and to the different versions if you want to review how to go over the different steps and processes that we are describing here. So I posted the link on the chat. We're gonna start with our presentation right away. Just one second. So if you go to that link, we're gonna start with module 1.6 version 0.1. That is the one where we stopped at yesterday. So we're gonna start from that one today. And I'm gonna do a quick review of what we did yesterday. The idea that we've been working with is how to specialize OD models in CC3D and why. And I've mentioned a couple of times that ODEs are extensively used, especially for understanding infectious diseases, but in general for understanding biological systems. And they can be powerful tools because they can be readily fit to the data such that the parameters can be estimated and the model can be used as a predictive tool. However, these ODE models do not include heterogeneity in the population and doesn't provide spatial resolution. And for some diseases, these spatial temporal dynamics and the stochasticity associated with individual agents is necessary for predicting disease outcomes. So that is a motivation to take these ODE models and then put them in a spatial context. The first thing we worked with yesterday was initializing at least in this module, in the previous module, we imported the anti-money model to CompuCell, so it's available for us, and it's gonna guide our cellularization, and it's also gonna help us make sure that as we implement each cell transition, that we are tracking the corresponding cell population in the OD model. The first thing we did in this module yesterday was to initialize our cell sheet, our epithelial cell sheet, and we talked about how to iterate through the cell domain, to the simulation domain, and then locate cells at different locations in the simulation domain. And what we end up with is a one-dimensional layer of square cells that look just like the image in the presentation. We also then once we have that epithelial sheet, then we can start implementing transitions between the cells in that layer. And we talked about how we can use the rate equations in the ODE model or the anti-money model to determine the transition probability for independent cells, for individual cells in the cellular model, such that I use a rate equation that goes from uninfected to infected in the ODE model, to determine the transition probability for infected individual uninfected cells in CompuCell to infected cells. And we use that by translating the rate equation into a Poisson distribution. Yesterday, we were able to implement the specialization. We actually went all the way to virus releasing. No, I'm sorry. We implemented the transition from, we finished implementing the transition from uninfected to early infected. And we also started implementing the transition from from infected to late infected or virus releasing. And what we get at the end of that, of yesterday, this is where we ended yesterday, is that we can, at this point, we can match the cell curve corresponding to the uninfected cell population, and that we can also match the curve corresponding to the early infected population. And the exercise we finished with was to finish this, these cell transitions by implementing the transitions from virus releasing to dead cells. And that is the version of the code that I've provided, ends up right in this step. And now we're gonna start working from that version to implement the next transition, which would be late infected to dead. This was the exercise, and we did it twice yesterday. I'm gonna review what the idea of the workflow for implementing these type transitions is. And the idea is that we start by, number one, determining the transition probability using the rate equation. And we do this in the step function of the steppable class. In this particular case, the rate transition is given by D times the number of virus releasing cells or I2 cells. So we can use that D to estimate the probability that one individual cell is gonna transition from virus releasing to dead. And we also talked about the fact that we need to scale our ODE models with respect to the time scales and the spatial scales of our CC3D simulation. And I mentioned that we are not gonna go into the details of when to use the scaling factors, but this is something that people that are interested in, and a couple of people did reach out to me yesterday. If people are interested in learning how to do this in a more systematic way, don't feel free to reach out. After determining this probability, then we have to iterate through our list or our group of virus releasing cells. And we do that by coupling the Python iterator with the list of virus releasing cell. And this is taken from the CompuCell library. And once we are iterating through each of the individual virus releasing cells, then we roll a dice to determine whether the cell is gonna transition or not. And we did talk a little bit about what rolling this dice meant yesterday. If this condition is met, then we change the cell type of the cell. So the cell, that individual cell, it's gonna now become a dead cell. And then we reviewed the flow of the workflow for adding data cities to our existing plot windows, how to count the number of dead cells and virus releasing dead cells. And we do that by measuring the length of the list of virus releasing, because the list of virus releasing cells contain pointers to each of my virus releasing cells. So if I count the number of pointers that I have, then I know how many virus releasing cells I have in my simulation. And last, we add this, we add the data points to our existing window, such that we can compare now the ODs to the cellular version. And I'm gonna explain how do we implement this in the code. We basically, let's first launch, let's first open the version of the code that I sent you. So we launched NanoHub, we launched CompuCell in NanoHub. Once we are in the CompuCell tool, we open to edit by clicking File, Start to Edit. And just a reminder that we have to upload the files to NanoHub using the Jupyter tool. So that is the way we're going to have the files available to us. The next thing we do is we are going to open the project. We're going to open the CC3D project. I go to CC3D project into it, and then I click on open. I have to go to my local directory in NanoHub, which I access by going to computer, the root directory, and then home, NanoHub, and my user directory. And then in preparation for this class, I have already uploaded the modules that we're gonna be working with today. The one we're gonna be using for this section is gonna be module 1.6. I hit open. To edit, it's gonna unzip the file, and then I can come back and open the project now. That is gonna be inside this folder. And it's gonna be, the file that I wanna open is the glacier model.cc3d. And then yesterday we talked about the different, the file structure associated with CompuCell projects. We're gonna go, in this case, we're gonna go to the steppable file. And here is where we implemented all of the transitions. If I go to if I go back to CompuCell, I can launch this project by clicking File, Open Simulation File. Again, I have to go back to my home directory in NanoHub and locate the same glacier model CC3D file inside the module _ 1.6 version 0.1. When I open that file, I can hit play, and this is gonna show the simulation where we stopped at yesterday. And it's tracking both the OD model and the CC3 model. So the idea is now that we want to implement the next cell transition. The first step, as I mentioned, is to determine the probability of infection. And we do that in the step function. And we're gonna do it before, let me move this a little bit this way. We're gonna do it before the transition between infected and virus releasing. This is gonna be, we're gonna call it viral killing. We're gonna come later. I'm gonna discuss here in a second why we're doing this. And then we have this death rate that we mentioned is specified by the model parameter. And we should remember from yesterday that this specific syntax allows me to access the dictionary associated with the anti-money model, such that I can access the values in that model. And the way I do it is by specifying the specific variable or parameter in that model that I am interested in. So scale by time. Again, we're not going to worry too much about when to scale the parameters, but it's definitely important. Then we can, once we have that rate, we can determine the transition probability, which is given by the Poisson distribution. And then now I have determined the death rate and the transition probability from that death rate. Next thing I need to do is I need to iterate over my virus releasing cells, because those are the ones that are going to transition. And I do that by coupling the Python iterator for with my cell list virus releasing. And I explained yesterday that if the specific syntax to iterate through your cells, you can get them from the threaded snippet available template codes at CC3D Python visit all cells of a given type. And it's gonna provide a template that looks just like this, and we'll have to modify it such that we can iterate through the specific cell types that we're interested in. Once we're iterating through the virus releasing cells, now we can roll the dice and compare to the death probability. We explained yesterday, we're not using NumPy in this case, we're just using the random function because we have imported the random library already. And the way we compare numbers or condition, or the way we establish conditions in Python is by using the if operator, and then we compare the random number to the death probability, and the random number has to be smaller than the death probability for the transition to occur. If the transition occurs, then we can change the cell type of the cell, and we can access and manipulate attributes of cells by, we can get the templates to manipulate attributes of the cell by going to CC3D Python, cell attributes, And in this specific case, we are interested in cell type. And I did talk a little bit yesterday that this snippet code explains that we have both writing and reading access for these variables. So meaning that we can read off the value or we can change the value. And in this case, we wanna change the value. So we change the type of the individual cell I am iterating over, which is denoted by this variable, to, and just a reminder as well that cell types in CompuCell are always specified in all caps. So that establishes the transition between my dead cells, between my virus releasing and my dead cells. The next step is to actually plot the data so we can compare the population of dead cells and virus releasing cells in the ODE model and the cellular model in CompuCell. And the way we do that is we go to the star function where we have defined our plots. We have a specific window that contains the data, that displays the data of the cell population. And we already have a couple of data series associated with that plot. Specifically, we have the number of uninfected cells, and we have the number of, let's see if I can zoom out. Okay. And we have the number of infected cells. Now we want to add the number of virus releasing and the number of dead cells. And we can copy the snippets from yesterday to be able to, and then fill them up with the specific data that we need for the versions that we're gonna be, the data series that we're gonna be plotting now. The first data series that we're gonna plot is virus releasing. And just again, a quick reminder from yesterday, this part refers to the handle, to the plot window. It needs to be the same as the plot window I wanna add that series to. The add plot function creates the data series that I want to add. Then I have to name the data series, and I have to choose a specific plotting style. It can be lines, it can be dots. There's other options as well. And we have to choose a specific color for it. In this case, we're gonna plot them in green, and a size of the marker that I had already defined from yesterday. So now I have already added the virus releasing cells as a data series, but not yet any data points. I can add the next data series, which in this case is gonna be the dead cells. And again, the styles is gonna be dots. For convention, we're using lines for the ODE model and dots for the cellular model. So we're able to, that way we can distinguish which data corresponds to which model. Then we can modify the color. In this case, we're gonna plot them as yellow. Then, and this is all we did yesterday for infected, uninfected, and infected. Now we're doing it for virus releasing and dead. So now I can come down and count. To add the data points, I need to count how many cells of each type I have at a particular simulation step. So I have to go to the step function, and then I can add the number of, I can count the number of virus releasing cells and the number of, I'll do it with down here with the same, with the group of what I'm counting the other group of cells. So I talked yesterday, as I mentioned before, the way I can count how many cells of each type I have in CompuCell is just by measuring the length of the particular cell list that contains those cells. So in this case, I'm interested in counting the virus releasing. So I'm going to be counting the virus releasing. I changed the name of the variable I'm storing that quantity in. And then I get the length of the list, but in this case, it has to be the list of virus releasing cells. Okay, and I will do the same for the number of dead cells. It's gonna be the number of cells dead, the length of the list, but in this case, dead cells. Again, I can use that list to iterate through each cell, but I can also count how many of those cells I have by measuring how big that list is. And then the last step is to just add the data points to the data series that we just created. And we do that with using this syntax, or we can get it from our template snippet codes that we get from CC3D Python, scientific plots, and then add data points and specify that it has to be in the step function. If I do that, I'll have to modify the, I'll just show it. It provides a template for adding data points that we have to modify so we make it specific to our simulation. The first thing I need to modify is the handle, so I can add in the specific window that I want to add. The next thing I have to change is the name of the data series, and we call them virus releasing and dead. We mentioned yesterday that we are not interested in plotting in terms of the simulation step, but actually in terms of the model steps. And we have a conversion factor that allows us to translate from one to the other one, which is our conversion factors days to MCS. And then now I can just add the two variables where I'm storing the two variables where I'm storing the number of dead cells and the virus releasing. Gonna be And okay, once we done that, we have completed the exercise that we were intended to do yesterday. And we can actually, yesterday, as we were building the model, we commented out some of the data being plotted in the plot window from the ODE model, because we wanted to be able to compare one curve at a time. So now we do have the virus releasing in the ODE model, in the cellular model, so we can put back the virus releasing and the dead. And the way I uncomment is I go to edit and I click block uncomment. So in principle, I should not now have the plot for the ODEs and the cellular version. Okay, so someone is asking for an explanation again. Oh, hold on, I just need to scroll to it. Right, an explanation of the line corresponding to the probability of cell death. This one, it's 144. So as I mentioned, the idea is that we are estimating the probability of cell death from, and actually I have a typo here. The probability of cell death from the rate in the ODE equations. So let's go back here quickly. The death rate in the ODE equation, the rates in the ODE equations are describing changes in the model variables, in this case, cell populations. However, we need to somehow use those rates to estimate the probability that an individual cell is going to transition from one state to the other. And the way we translate rate equations to transition probabilities is by using the Poisson distribution. So we take 1 minus E times the rate equation times dt. So that's why what we're doing in line 144 is that we're estimating the death rate, the rate associated with cells dying in the ODE model, and we're turning that into a probability that we can apply to individual cells in our model. Okay, so the idea, once we finish all of this, we can come back to our simulation, and if we don't have any syntax errors, which are totally common, and I always have, one second, we can read off the syntax errors from the console. It's telling me, right, that I didn't save when I correct the typo the last typo that I had. Okay, another typo is that I don't have the number of virus releasing cells when I am trying to plot them. I'm not gonna get stuck in solving small syntax errors because we have a final version of this code that works, and we can just go ahead and run it. But let me see if I can fix that one really quick. Yep, it was a typo. Okay. Good. So now we have all of our cell types implemented in CompuCell. All of the epithelial cell transitions implemented in CompuCell. So we're gonna let this running in the background because I wanna, so we see there are quantities in the CC3D model, which is this one. There's transitions between cells that we're looking at here to track pretty closely the transitions in the OD model, which are overlaid on top of each other. Okay. I'm gonna give people a minute so they can actually, if they're working through the code, they can finish implementing it and solving any syntax errors that they might have encountered before moving to the next part of this. Let's see if there's any questions in the meantime. Okay. Yeah, if people have any questions so far, this is a good moment to ask before we move on to the next part. Okay, so while that runs in the background, what's gonna happen next is if we let the simulation run for some time, this particular simulation, at some point, the OD and the cellular model will not track anymore. I want to see if anyone has a guess of why is that happening? Why it stops tracking pretty much after day 4? If you have a guess, feel free to send it over on the chat. Okay. So if we go back to the big code, the big model, let's go back to the big model. In the big model, we have cells transitioning from uninfected to early infected, from infected to late infected, or what we're calling virus releasing, and then from infected to dead. But there, in the original model, there's actually 2 mechanisms by which cells transition from virus releasing to dead. One is just because of determined by the rate parameter D, which is associated, as James was describing in his module, is a representation of the activity of the innate immune response, either cells dying because they have too much virus inside or some immune response associated killing. innate immune response associated killing. But we haven't incorporated yet any adaptive immune response. And the difference that we're seeing in our model at the moment arises from the fact that we haven't yet included the killing by adaptive effector T cells. And what we see is that we in the cellular model, which is the dots here, we get less cell death than in the OD model. Okay. So what I'm not gonna actually I'm gonna explain how we can quantify the death mechanism, how much death you're getting by each mechanism. We're not gonna code it because it's just basically a little bit repetitive of what we've done so far, just counting and adding plot windows and data cities and data points. But the next version of the code, the version 2.1, it's gonna have that already implemented, what I'm gonna walk you through, guys. So then after class, if you feel like practicing implementing more code, you can come back to this slides and then try implementing what we will be walking through here. So again, as I mentioned, the difference that we are observing between our OD model and the cell model arises from the fact that we haven't integrated the adaptive immune response yet. And TJ is gonna explain us how to do that later today. One way we can quantify what each mechanism, how the amount of that each mechanism is contributing in the model is to actually quantify, distinguish basically distinguishing how cells that are dying because of innate immune response and cells that are dying because of adaptive immune response. And we have already included in the OD code in the anti-money model a additional piece of code that allows you to distinguish between those two, between cells that have died because of innate immune response and cells that have died because of adaptive immune response. And the idea is that we can also quantify that in our CC3D model. And the workflow is the same. We create a new plot window. In this case, it's gonna be the death data plot window. CC3, the way we access this piece of code is CC3D Python, scientific plots, and the start function, we have in the start function, we have how to set up the plot. And then we specify that it's gonna be that data that we're gonna be adding two data cities, how much cell death we're getting because of the innate immune response, which we're calling here vital ODE, and because of the adaptive immune response that we're calling contact ODE. Then we count from the ODE model how much cell death we're getting by each mechanism. We have conveniently included variables in the anti-money model that distinguish those two. And then we can add those data plots to our model. And then when we add those data points to our data cities and our plots, and then when we run CompuCell again, we will get a new window that is gonna show how much cell death you're getting in the ODE model because of each cell death mechanism. To do that in CompuCell, we created a new dictionary that we're gonna use to store how cells are dying in CompuCell. And then every time a cell dies in CompuCell because of this cell death mechanism, we increase the number of cell death in that dictionary. And the Python operator plus equals allows you to take one value and increment it by the value that you specify. So basically, every time a virus releasing cell transitions from virus releasing to dead because of the innate immune response that is represented by this parameter D, we increase the count of cells that have died because of that mechanism. Again, same workflow, we add the data series to be able to overlay the ODEs and the CC3D simulations. And then we can plot the values, the number of cells that have died because of this mechanism using the key in the dictionary that we created. And the key is gonna be viral. And then lastly, when we plot all of these together, what we see is that at the beginning of the simulation, because there is very small amount of killing associated with the adaptive immune response, our model tracks really well. But as the amount of killing associated with the adaptive immune response goes up, our model starts differing from the ODEs. And we can see that in the ODE models by this time, by day 7, almost all cells have already died, whereas in the ODE model, we still have virus releasing deaths in the simulation. Okay, I did not want to code over the code because it was basically just creating plots. But if we want to access the code that has all of what I just walk you through implemented, we can come to NanoHub, and we can intuit it. We open a project, and instead of using version 6.1, we load version 2.1. I'm sorry, instead of using version 1.6, we use version 2.1. And version 2.1 should have the code that I just walked through implemented. Now I have the death mechanism plot, and I am counting every time a cell dies. Now I can launch it in CompuCell. I need to stop the simulation to open a new file. File, open simulation, go to my home directory in NanoHub. Then I can load version, the module 2.1 version 1. And when I execute that code, now I get all of the windows that I just explained in the simulation. I'm sorry, it's gonna be, yeah, yeah. Let's see, no. Yeah, it's there, it's just hard to display it. Maybe it's displaying better in your computers. But the window should be available for you now. Okay, and if there's any questions related to this particular part, I was just walking through it quickly, again, because it was just a matter of implementing, of putting on, creating new plot windows, but it's a good exercise if you guys wanna work on how to, or refresh yourself how to implement plot windows and data cities. Okay, so this is the end of module 2.1. I'm gonna stop here. I'm gonna give everyone 5 to 10 minutes to load what we're gonna be using for the next module, which is 2.2. In that case, it's gonna be, we're gonna start from this version, the version that I just loaded in Tweeted, which is version module 2.1 version 1. We're gonna start at that simulation. If there's any questions, also feel free to ask. The seed version 2.1 is in the same folder. In the same, I'm posting the link in the chat. You can go there, and it's gonna be module 2.1 version 1. Gonna stop sharing for a second, and I'm gonna take 5 minutes to load everything for the next module. And if there's any questions in the meantime, please feel free to reach out in the group chat.